Good afternoon, everyone. So my name is Riku Jäntti, and I'm professor at Aalto University, Finland. And I will give a talk on sustainable zero-energy machine-type communication for 6G and beyond. So I will first start with the part related to 6G, and then move to this beyond part. So the zero-energy devices is something that has been now been discussed in the 6G context. So this picture I took from Ericsson material, which shows that okay, you have the NR, then there is the plan to have this reduced capacity and version of that. You have LTE-M and NB-IoT 5G machine-type communications. And now when we are moving towards 6G, there has been also this discussions of having even less capable but less energy-consuming devices called zero-energy devices. And so those devices would harvest the energy that they need from ambient sources. And it could be basically battery-less devices, so maybe just have a supercapacitor to power the device. So really the aim is to have devices that consume very little power so that the energy harvester can support them. So there's just some numbers from a couple of different papers. So one is the sort of transmit side. So having really low power, so-called ultra low power transmitters. So one way of doing that is to use backscatter communications. So in that case, you don't have to have a local oscillator at the device, and you don't have a power amplifier at the device. So the device just communicates by changing the reflection coefficient. And this is from one paper from 2017 from the University of Washington. Comparisons of how much power is consumed by active radio transmitters and how much power is consumed by backscatter devices. So we have like orders of magnitude less power required. Then of course the zero energy devices would need some sort of receivers as well. So for that I guess the current research direction is to look at this kind of so-called wake-up radios. And those also have really low power consumption compared to the current traditional receivers. But my presentation today will actually focus on the transmitter side. So using backscatter communications, in backscatter communications, in classical backscatter communications like an RFID tag gate, there's some device that transmits unmodulated carrier, and then this backscatter device modulates that basically by performing so-called load modulation. So it changes the impedance, which causes the reflection coefficient to change, and in that way modulates the signal. Then that is a little bit energy inefficient because we need to still generate carrier signal, but to get even more energy efficient is to use so-called ambient backscatter communications, in which you have modulated carriers. Maybe the echo vanished, so I can continue. So in ambient backscatter case, we have some modulated carriers, so some signal that is actually being transmitted by some cellular system or TV or some Wi-Fi. And now this backscatter device actually modulates that one. So then there's just a challenge at the receiver side then to try to demodulate that backscatter modulated signal. And this kind of concept can some noise.
Excuse me, the slides are not moving. If you are planning, the slide is still in the first page, the topic slide.
So the slides are not changing?
No, we are still in the first slide.
See what I can do about that.
share screen. Share screen. Top one, yes. No, the top one. Yes.
Yeah, it's not showing the on the remote place.
Now they should be able to see.
Are you able to see now the slides?
Yeah, we are in a different slide now, so.
Okay, good. Let's hope that it continues. Yeah. So this ambient backscattering communication system scenario can be combined with mobile communication systems, and one potential scenario is this, what was suggested by Orange, the operator in France. It's so-called crowd detectable zero energy devices. So now they use the cellular generated signals. There's for instance, in downlink direction, the base station is transmitting a signal to the UE, and the UE, while it's receiving that signal, it also tries to receive the backscattered signal. Or it could be done in the other direction as well, so that the UE is transmitting, and then the base station would need to try to decode the backscattered device signal. And as an energy source, this Orange concept used solar cell. In RFID, it uses the RF power, but if you use RF power, then the range becomes really limited because the energy harvester requires power levels of something like minus 30 dBm or something like that, which is really high. So hence, it's better to decouple communications and energy source. So with ambient light, then there's at least sufficient energy. Actually, there is sufficient energy, maybe even to run active devices. But in this case, just running this microcontroller basically with the solar cell that does the modulation of this backscatter device. Stop showing. Changing the slide here as well. So, what kind of ranges we are talking about if we are using this kind of system? So we have done some ray tracing simulations. We used downtown Helsinki as the model, and used the existing cell sites there in new places, and then look at what kind of distances could be supported, or basically simulated what is the received power level in different locations on the street with different carrier frequencies. So this minus 120 dBm, this may be something that might be quite realistic. This minus 149, which is the other line, is kind of the LoRa sensitivity level. So depending what kind of receiver sensitivity we manage to get, then of course we have different kind of ranges, but it's more conservative, minus 120 dBm. Then with 900 megahertz carriers, if we are just outdoors, then we are talking about tens of meters of range. But then if you go indoors, then there's challenges that there is quite large attenuation from the walls. So there's low and high here. It's just referring to different kind of wall attenuation. So in modern sort of high energy efficient housing, the attenuation is much higher. So then we are talking about some few meters of range between the backscatter tag and the UE receiver if you go indoors. If you are operating at 900 megahertz, and then if you go to something like 700 megahertz band, then we can have maybe 10 meters or more of range. And of course, if you would be actually using this kind of systems in really low frequencies like 500 or 200, then the indoor use cases would be better suitable. But those are challenging then also from the antenna side perspective. Okay. So to see how this kind of system could be then implemented. One way of doing this is that we have the receiver, so we have the UE just using an existing mobile device and modify its channel estimator. So this is an example of an LT downlink case. So there's a transmission of self-specific reference signals, which are present even if there is no data. So they are sort of always present there. So we utilize those then to kind of just to sense the channel. So the backscatter device modulation would be now present in the channel estimate. So we would have variations in the channel estimate because of backscatter device. So and implemented this kind of receiver and tested it. So the software-defined radios in the lab to see how it works. So here we had kind of an indoor pico base station. So basically it's just a signal generator making the LT frame and then software-defined radio receiver that implemented the LT channel estimator. So in this setup we saw that okay, it was feasible for this kind of devices with, to really see the backscatter device signal on this from the channel estimate. The main challenge is that if you look at how we sample the channel, we get only like in time the sampling rate is pretty low, so that limits the kind of data rate of the backscatter device, and then so there are so this one in LT is we have like 4 samples in 1 millisecond, so 4 kilohertz sort of sampling of the channel, which sets this 2 kilohertz as the maximum basically that we could try to modulate the signal, and then the other thing is that we need to modulate the backscatter with the backscatter device the signal fast enough so that we can separate it from the natural Doppler component. So there's kind of a spectrum where we can place our backscatter device. So it's basically from the receiver perspective, it looks like additional multipath component, but it's much higher Doppler. So that was just showing that this kind of devices, the zero energy devices, could be integrated into cellular systems rather easy just by modifying. From the receiver perspective, it just requires modifications in the firmware of the UE devices. One challenge with all kind of IoT devices in general is sustainability, and I have this sustainability also in the title. So actually, we are currently generating a lot of electronic waste. So in 2016 it was 15.
Recording in progress.
4.7 million metric tons, and it's increasing all the time. And now we are making this kind of very cheap devices like what we talk about here. Zero energy devices would be also low cost devices, which means that they would be there is a kind of temptation to put them into also quite cheap products. So there already are IoT products like intelligent basketballs that have Bluetooth chips in them, and they, I mean, you can't really change the battery inside the basketball. So once the battery runs out, that becomes a waste. So there are this kind of applications in IoT devices that there's kind of a challenge that on the environment. But if you talk about this kind of simple backscatter devices, they actually can be implemented in quite environmentally friendly manner, basically using printed electronics. So there already exist on the market printed RFID tags. So the antennas can be printed, and then there is a small chip. And then depending on how this chip is packaged, then basically this kind of harmful electronic waste can be avoided. And in principle, it would be possible maybe someday to print the whole device. So you could print basically those backscatter devices on some cellulose-based substrate, so that at the end of the life cycle, there is no really anything harmful to subsidies left. So it can be completely recyclable and in that sense reduce this e-waste problem. So to summarize this sort of 6G part, we have this ambient backscatter communications is quite promising technology for ultra low power communications, and in the 6G context, we could use the cellular signals as the ambient signal, and basically then integrate the receiving of these backscatter devices to just channel estimators of in the UE. And depending on how we do this backscatter modulation, it actually is seen by additional multipath components for the UE. So the interference is either very small or can basically be avoided. So it's also kind of a spectrum sharing technique. Okay, so now let's talk about a little bit even beyond 6G applications of backscattering. I mean, backscatter communications in principle is just an application of radar technology for communication. So then we could go to one step further and start looking at quantum radar. So quantum radar, which basically generates entangled pair of microwave photons, and one of them is utilized to check if there's an object there, and the other one is kept at the receiver, and then joint measurement is done to receive them. Actually, quantum radars in the microwave domain are quite challenging devices, and they have quite short range, so they might not be that immediate boom for radar technology, but this range problem is not so critical for backscatter communications, where the ranges are smaller anyway. But in principle, at least in the lab, the technology for generating microwave photons exists. So this is kind of technology in that sense that can be tried out. So generating microwave photons actually requires this kind of a superconducting chip. So the transceiver, so this is not ambient backscatter. You really need to generate the carrier and receive that in one place. So this is just backscatter. And to do this microwave photon generation, it requires these superconducting devices that operate in 20 millikelvin temperature. So those need to be in a really low temperature. But then once the photon is generated, it is taken out and then interacts with the object. So in this case, it would be utilized for communications, for backscatter communications, where now the backscatter device is just modulating, basically either absorbing or reflecting back the device, the photon that was transmitted. So, okay, just in principle, if you look at what is the gain of doing this kind of thing, well, it would give 6 dBs SNR gain, but that's like not really where the main application is then to use it for secure communication. So in principle, it's possible now to use this kind of device set up to hide the existence of the backscatter communications in a way that it is impossible even for almighty eavesdropper that basically can fully control the environment to detect that the communications took place. Okay, so just to conclude my talk, so there are two parts. First one was the 6G part without any quantum. So just using the cellular signals together with backscatter communications, and then build these backscatter devices using sustainable methods like using printed electronics, so that we minimize the e-waste. And the same backscatter device can be used in this quantum case as well. So the communicating device is classical. It's the same could be even the same printed tag. But then in the whatever beyond 6G case where we would use the quantum to make it really secure, then the reader would be implemented in the characteristic bridge using the superconducting devices. And if you would do that, then we would actually be able to make it really secure. It's impossible to anybody even to detect that we were really backscatter that. Okay, so this concludes my talk. So if there's any questions.